Now I request Dr. Safina Devi, Assistant Professor of Mathematics, to welcome the gathering.
Good afternoon, everyone. A warm welcome to our Honorary Secretary, 3AP C.V. Chokkalingam Sir, and our beloved Principal, Dr. C. Veerababu. I extend a hearty welcome to our Chief Guest, Dr.S.Uma, Head and Assistant Professor of Mathematics Department, Government Arts and Science College, Kallakurichi. Welcome, ma'am. And a warm welcome to all the participants gathered here for today's program over Google Meet and YouTube. Welcome you all once again. Over to you, ma'am. Martina, ma'am. Thank you.
Thank you, ma'am, for the warm welcome. Now I request Dr. L. Pondiselvi to introduce our resource person.
Good afternoon, everyone. It's my distinct honor and privilege to introduce our resource person for today, Dr. S. Uma. She is working as an Head and Assistant Professor of Mathematics, Government Arts and Science College, Kallakurichi. She completed her PhD from V.O.C. College in 2018 under the guidance of former HOD Dr. R. Balakrishnan and focused on near rings. Her research work has been recognized through numerous publications and presentations in various conferences. In addition to her teaching responsibilities, she has played significant roles in academic administration, including serving as the Chief Superintendent of Examinations, Board of Studies members, and Assistant Controller of Examinations. Her contributions to the academic community are truly commendable. She has also contributed as an internal ISO auditor. Her expertise spans a wide range of mathematics and computer science subjects. We are indeed fortunate to have you with us today as our esteemed resource person. Thank you, ma'am.
Good afternoon to all. Thank you, ma'am, for your nice introduction.
Thank you, ma'am.
At the outset, I would like to congratulate everyone in touch with V.O.C. College for achieving that 28th rank in NIRF 2024.
Thank you so much, ma'am.
Thank you,
Really, I
ma'am.
am happy to be a V.O.C.ian.
Yes, ma'am.
Yes. I really record my
Oh, proud
gratitude.
alumna, ma'am. You are our proud alumna.
Yes.
So very
Yes.
proud, ma'am.
Thank you.
Thank
I
you, ma'am.
really record my gratitude to all for inviting me to participate in this FTP as a resource person. Particularly, I thank Honorable Secretary Sir, Sri APCV Sokalingam Sir, Principal Dr. C. Veerabagu Sir, and Head of the PG and Research Department of Mathematics, Dr. C. Deva Manoharan Sir, and all the faculty members for giving me an opportunity to join with you. Really, I appreciate each and everyone in the PG and Research Department of Mathematics in V.O.C. College for their constant and enthusiastic research work, as well as organizing various programs to help the research scholars in mathematics across the world. I'm keenly watching the activities of V.O.C. When Dr. L. Pandiselvi, one of the organizing secretary of this FTP, approached me, I have decided to make this opportunity to turn many of the young mathematicians towards algebra. Really, I love algebra. Dear participants, as we all know, algebra is a unifying thread of almost all branches of mathematics, isn't it?
Yes, ma'am. Yes.
Yes, am I audible? Okay. 1 minute. Let me share my PPT first. Yes. To explore the beauty and the interesting aspects of doing research in algebra.
Ma'am, sorry for the interruption.
Yes, ma'am. Yes,
PPT slide வந்து கொஞ்சம்
yes,
full screenல இருந்தா நல்லா இருக்கும் மேம்.
Yes, I would
because
put
it has been telecasted in YouTube also. Thank you.
Yes, sir. Sure. Thank you. Just I'm going to discuss about some of the main features or some structures in nearings. Some structures to just motivate the young scholars or young research scholars and young faculty members to turn towards algebra. I'm making use of this opportunity. Shall we start? Algebra means playing with variables. Am I right? Under some conditions, we are going to play with variables. Let us start the session with some basic definitions. You all know, you are all faculty members. No need to take much time on this. Just refresh all these things. What is a group? To define a group, we need a non-empty set and a binary operation. Under that binary operation, if we are able to consider the closure property as well as associative property, means we call it as a semi-group. If it is if that set satisfies the existence of identity property as well as existence of inverse property, then we call it a group. To make it as an abelian group, we have to check for the commutative property. The another important algebraic structure is ring. To define a ring, we need two binary operations. Under addition, it has to be an abelian group, and as well as under multiplication, it has to be a semi-group. And it should satisfy two distributive laws, namely left distributive law as well as right distributive law. In the same manner, semi-ring, let us recall what is the semi-ring. To define a semi-ring, we need a non-empty set with two binary operations. And under addition, it has to be a commutative semigroup. Commutative semigroup with 0. Under multiplication, it should be a semigroup. For any three elements, A, B, C in S, it should satisfy both the distributive laws. For semi-ring, both the distributive laws should be held. Under addition, it has to be a commutative semigroup with addition, and under with 0, and under multiplication, it has to be a semigroup. Why I am repeating this means for the semi-nearing, we are slowly entering into nearing. Initially, I am saying about semi-nearing. Semi-nearing means semi, that means for instead of two distributive laws, we are going to concentrate only, we are going to have only one distributive law. That is semi-group under addition with the additive identity 0, and under multiplication, it is a semi-group with the right distributive law, means we call it as a semi-nearing. Okay, since the right distributive law alone is hold in semi-nearing, 0 into A equal to 0. 0 into A equal to 0. We can't say about A into 0. What about the result of A into 0? In the same manner, in nearing, we need a non-empty set together with two binary operations, addition and multiplication. Under addition, it is a group, not necessarily abelian. That is the main condition. First, we have to remember for nearing, n plus is a group, not necessarily abelian. Under multiplication, it is a semi-group, and right distribution law alone is going to be considered, means we are going to call that set as a right nearing. Am I clear up to this? Okay. What I'm going to cover in my speech or in my presentation is these things. I'm having an idea of covering these things, but that is, let me start with basic definitions and results in nearings. And then if time permits, we can cover all the things. Let us see. This substructures, what I'm going to see now. Basic definitions. before going in detail, let me introduce the notations used throughout this presentation. N0 is going to represent the zero symmetric part of N. N0 means whenever I say put N0, it is going to represent zero symmetric part of N. What is the meaning of that? That is in zero. If zero is the identity element, additive identity element, only right distribution law is satisfied. Therefore, I specified 0 into n is equal to 0, always true. But if n into 0 equal to 0, then we are going to collect those elements, that is collection of elements of n such that n into 0 equal to 0 means that is going to be called as zero symmetric part of n. And then if n is equal to n naught, what is the meaning of that? If all the elements in my nearing are having this zero symmetric property, that means if it n into 0 as well as 0 into n both are equal to 0 means we are saying that nearing is zero symmetric nearing. Zero symmetric nearing is nothing but in which n into 0 as well as 0 into 0 or both are 0. The next notation I want to introduce is ND, that is distributive elements I am going to collect. While seeing this definition, you can easily say this is nothing but left distribution law. N into x plus y. If it is true for all x and y in n means we are saying that collection of elements is nothing but set of all distributive elements of n. If that distributive elements is equal to, set of all distributive elements is equal to n means we are saying that n is distributive. An element, we are considering n is an element of capital. I'm repeating that distributive property only. ND is nothing but an element is having both right distributive law and left distributive law. If it is satisfying means this one case. Okay, if this is not equal to ring, you understand this. N is equal to ND means we are going to say that n is called distributive. Okay, let us pass on to the third definition, that is nilpotent and idempotent are defined as in ring theory. That is, if I am able to find a positive integer k such that a power k equal to 0, we call it as a nilpotent element. If a square is equal to a, we call it as idempotent. The next, some notations. Whenever I use the symbol a star, it is, we are negation of that identity element from a is denoted like this. C of a represents set of all commutative elements that that set of all elements of n that commute with all the elements of a, that commute with all the elements of a. And then center is nothing but we are collecting all the elements which commute with all the elements of n, that is C of n. Capital E denotes the set of all idempotents in linearing. Let us quickly go through this. I'm mainly concentrating on the theorems what I am expecting to show to you. Let us see the fifth definition, that is nearing n is said to be reduced if n has no non-zero nilpotent elements. Suppose a nilpotent element is existing means that is 0 only. That is the meaning, isn't it? N has no non-zero nilpotent elements means say that n is a reduced nearing. I put animation because of that. It is going fast. Okay. This nearing n is said to be regular if for every a in capital N, I am able to find an element n capital N in the name of X such that A equal to AXA. That is A equal to AXA. That is every element of N can be written in this fashion. For some X means we call that nearing as regular nearing. Mainly my talk is going to be on regular nearings only. Remember this. Insertion of factors property, that is IFP is the 9th definition. That means whenever AB equal to 0, implies A and B equal to 0. That is, I'm inserting an element between A and B, still the answer is 0. It is valid for all the elements of N, means it is going to be an insertion property. That is, N is said to fill the insertion property if it satisfies this. In addition to this, if AB equal to 0 implies BA is also equal to 0, means we say that N has star IFP. That is another definition. Strong IFP is nothing but whenever XY is in an ideal, then XNY is also in the same ideal. If it is true for all the ideals of N, means we call such a nearing as strong IFP. That is, for strong IFP, we are dealing with some ideals. For all the ideals, if the result is true, we are saying that it is N has strong IFP. Substructures means mainly we think of ideals as in ring theory. Substructure, important one, that is right ideal is defined as in ring theory. That is I plus must be a normal subgroup of N plus. And if In is a subset of I, it is going to be called as a right ideal. There is a difference in left ideal definition. Can you notice that? That is, since the left distribution, okay. Since the left distribution law is not hold in our nearing, we can't directly define Ni is a subset of I. Instead of that, how we are defining I plus is a normal subgroup and N into N dash plus A, where N and N dash are elements of capital N. A is an element of our ideal. Imagine if it is a ring, I can multiply N dash plus NA. What is going to be the result? N dash and N dash will get cancelled. We will end with Ni is a subset of I. That will be the answer. Instead of that, in nearing, no left distribution law is not valid. Therefore, we are defining left ideal in this fashion. If both are true, in that case, that is right ideal as well as left ideal, both the conditions hold, means we are saying it as an ideal. As in ring theory, we are having different types of ideals: prime ideal, semi-prime ideal, completely semi-prime ideal, completely prime ideal, strictly prime ideal, and primary ideal. Maximal ideal also we are having in the same sense. Okay, the ideals quickly let us recall. Another important structure in nearing is N subgroup. N subgroup we are defining in a nearing in this fashion. A subgroup M plus of N plus is called an N subgroup if N M is a subset of M. We are selecting one subgroup M. If it satisfies Nm is a subset of M, we call it as an N subgroup. Principal N subgroup, like principal ideals, we are having principal N subgroup, that is Na. Instead of M, I am selecting any element in there from the nearing, that is Na is an N subgroup. Invariant N subgroup is defined. Invariant, that is, other than that N subgroup, in addition to that N subgroup condition, it satisfies M and it's also a subset of M, means we are saying that is an invariant N subgroup. Another important structure is subnearing as well as invariant subnearing. For that subnearing, we have to check whether MM is a subset of M. mm is a subset of m as well as if it satisfies all the conditions of invariant n subgroup, that is mn subset of m as well as mn subset of n subset of m as well as m subset of, sorry, it is going where? Sorry. Invariant subnearing. If m is a subnearing of n, m should be a subnearing. That means mm's should be a subset of m. Other than that, mn subset of m as well as nm subset of m. If all the three are true, we are saying that invariant subnearing. Okay. Am I going fast? Since these are basic things, I couldn't see the chat box. Can someone on the speaker and say, am I going fast?
No, ma'am.
Okay, that's it.
Okay, ma'am. Thank you.
Thank you. Some basic lemma, that means some important results in nearings. Based on the nearings, we are going to prove many of the results in nearing. The basic things we have to remember whenever n is a zero symmetric nearing. If it is a zero symmetric means, I already explained, can you recall that? That is n into 0 is 0 as well as 0 into n is 0 means we are saying that nearing is zero symmetric nearing. In such a nearing, left ideal is an n subgroup. That is the first result. Every left ideal A of n is an n subgroup of n. Similarly, every ideal satisfies n is a subset of okay. The lemma 4, let us say, under subcommutative nearing. That is subcommutative, we have seen. Can you remember that subcommutative property? That is, let us go back and recall. These are very important concepts. That's why I once again come back. Sixth one, subcommutative. Nx is equal to xn. For all x in n means we are saying that nearing is subcommutative. And at the same time, let us recall V-commutative also. In that V-commutative, xyz is equal to xzy for every xyz in n. Can you identify that? The first element is fixed. The second and third element interchanged their position. Okay. V-commutative defined on three elements. XYZ is equal to like that. Subcommutative property is defined in with set nx is equal to the set xn. If those sets are equal, then we are saying that subcommutative. Okay. Sorry, take a rest. Okay. This one, second lemma, whenever n is zero symmetric, reduced nearing, where I left, this one, isn't it? Some interruption occurred, I forget. Okay. Second lemma, zero symmetric, reduced nearing. Reduced means there is no non-zero nilpotent element. In that case, ABE equal to AEB. E is nothing but an idempotent. A and B are elements of n. Second, I think we have discussed about this, I think, isn't it? Okay. If n is a zero symmetric reduced nearing the same condition, in that case, when A equal to B, we can say means AB equal to B square and BA equal to A square. If that result is true, means in that case, we can say A equal to B. This basic result we need in most of the results. That's why I have recalled those things. Lemma 4 depends on the idempotent as well as subcommutative nearing. In a subcommutative nearing with identity means NF plus NE, where E and F are idempotents. I can write it as in the form of N into, with identity we have considered, therefore 1 minus E is defined, 1 minus E into F plus E. Okay, if N is a subcommutative nearing, this result we are having. Similarly, in the same condition, N is a subcommutative nearing with identity, and M and P are two subgroups in N satisfying these two conditions. That is M plus P equal to N and M intersection P equal to singleton 0. That is nothing but what we can say. M circle plus P is equal to N. In that case, we are able to get what result? M is equal to NA and P equal to NB for some idempotents. That is very important. M and P are going to be principal N subgroups with the help of some idempotents A and B. M and P are going to be principal N subgroups. Okay. Now, slowly I have entered into one structure in nearings. Initially, stable nearings were defined. After that, substable nearings. Similarly, we can continue this in this. Many researchers got going on. That is substable nearing. When we say a nearing is substable nearing, means if I am able to find a stabilizing subset F. What is the condition for a stabilizing set? Means F should be not equal to singleton 0, and it should satisfy xf equal to xfx equal to fx. If these three sets are equal, xf equal to xfx equal to fx for all the elements x in En. In that case, that is stabilizing subset. If such a stabilizing subset exists in my nearing, means we are saying that as a substable nearing. In that substable nearing, we need some regular subset to get some results. That's why we are searching for this definitions. What is that? Partially invariant. Already we have defined N subgroups as well as invariant N subgroups. In what manner? Mn is a subset of M as well as Mn as well as Nm. Instead of N, we are using F, that is our stabilizing subset. Like that, one subgroup M plus of a nearing is partially invariant if Mf is a subset of M and Fm is a subset of M. Okay. F subgroup, how we have defined N subgroup, we compare it with that. N subgroup means we say that M is a subset of M. F subgroup, therefore Fm is a subset of M. Okay. Regular nearings we have defined, that is for every A in our N. I can write A is equal to AXA like this, means we have defined for all the elements of N. Here for the subset A, within the subset I can find an element X. Within the set itself, I can find an element X such that A can be written as AXA, means it is going to be a regular subset. Sorry. Okay. That theorem on point 1 is some applications. That is applications in the sense the near upcoming theory, we are going to use it. That is, if N is substable, then set of all idempotents is a subset of C of F, means set of all commutative elements with F. Okay. That means if N is substable, then E is a subset of C of F. The converse part is true only if I select yes invariant subgroup A, and if N is regular, then only the converse is true. But always we can think about E is a subset of C of F whenever we are taking N as a substable nearing. If N is a substable nearing, then E is a subset of C of F. Okay. Let us see how our definitions are used, how the proof is going on in nearings. I think going on with the definitions and lemmas, you may get bored or to motivate. I think it will motivate you. Let us see. If F is a regular subnearing, I have repeatedly mentioned what is regular as well as subnearing of the substable nearing. Everything we have learned. Okay. What we are going to prove, Fe equal to Ff is equal to Fg. Both E and F are idempotents. In that case, Fe plus Ff is equal to Fg. That G is also an idempotent in that first, okay, Fe plus Ff is equal to Fg, we have to prove. Okay. First thing, we have considered a substable nearing. If it is a substable nearing, then set of all idempotents are a subset of C of F. That is, idempotents commutes with the elements of F. That property we can use. With this property, I'm going to prove G is also an idempotent. What is G? G is nothing but E plus F minus EF. Therefore, G square, idempotent definition, A square is equal to A means idempotent. Therefore, G square we are thinking. E plus F minus EF. For this purpose only, we have defined F plus S abelian like that. Okay. E plus F minus EF, the whole square we have considered. If I expand this one, E and F are idempotents. Therefore, we get E square is equal to E, F square is equal to F, as well as they commute with the elements of F. Therefore, we will get, okay, can you follow this? EF and then this commute, therefore EF. Here also I can commute, therefore EF, like this. Therefore, some elements get cancelled. Okay, what are all get cancelled? Okay, simple calculation. Therefore, we are ending with G. That is, G is an idempotent. First thing we have proved. What we have to prove the next one? Fe plus Ff is equal to Fg. Normally, how will you do? We have to take an element in the left side and check whether it is an element of the right side set. Similarly, we will take an element in the right side and we will check whether it is in the left side set. In the same manner, we are going to select one element in the left side set. That is Fe plus Ff. Okay. That is Xe plus Yf. Okay, is an element of Fe plus Ff. For some x and y in F, we are taking an element. We are discussing in substable nearing. In the substable nearing, E is a subset of C of F. C of F means commutes with the elements of F. That is a subset of Fd. That can you understand? Fd. What is the notation for Fd? What it stands for? Fd is nothing but set of all distributive elements. Here it commutes means left distribution law, both the right distribution law can be used. That is the meaning of that, isn't it? We can write in any manner. That is, C of F is a subset of Fd. Distribution law holds since it commutes with all the elements of F. That is, x plus y into G can be written in the another way. G into x, E plus Yf. Like that also we can write that. That is that Fd we are using. Okay. Xe plus we are starting with an element Xe plus Yf into G. Okay. This one we are using right distribution law. Okay. Instead of G, we are substituting what is assumed. G is nothing but E plus F minus Ef. Now we are multiplying this side. Actually, in nearings, left distribution is not valid, but here E is a subset of FD. E is an idempotent element, therefore I can multiply. Okay, therefore we are getting these results. What we are going to get as the final result means XE plus YF. That is XE plus YF into G is nothing but XE plus YF. That is nothing but our element in capital FE plus FF lies in capital FG. One part over. Okay. The other thing, we have to take an element in FG and let us check whether it is in my FE plus FF. Can you follow how we are using that right distribution law alone and we are working? That's why I initially specified playing with variables with some conditions is algebra. Okay. Moreover, this one we are considering n is an element of f and ng is equal to gn. Sorry. Where to go? Ng is equal to gn. That is equal to, I'm substituting the value of g and we are multiplying. Okay. I think it is clearly written. We are multiplying. Okay. And then we are interchanging y. F is an idempotent. F is an idempotent as well as E is an idempotent. Therefore, it commutes with the elements of F. We have to verify this carefully in this substable nearing. That is, similarly, E and F are idempotents. Therefore, N commute with them and I am getting NEF. Okay. Now, F is common, like that we can take like this, N minus NE into F. N is an element of F. E is also an idempotent element. Therefore, we can say this is an element of F. Okay. N minus NE is an element that is of F. We got FE plus FF. FF. The other way also we have proved FG is a subset of FE plus FF. Therefore, we have completed this theorem. What theorem? Where I left. F is a regular subnearing of the substable nearing and F plus is abelian. Then for every idempotent elements, okay, idempotent elements F, E and F, Fe plus FF is equal to Fg. That G is also an idempotent. Based on theorem, we are generalizing that what we are concluding this in this corollary means if F is a regular subnearing of the substable nearing N and F plus is abelian in the same conditions, then instead of idempotents, for every xy in F, we are taking elements in F. In that case, I can find an element Z in F such a manner Fx plus Fy is equal to Fz. It is going to satisfy this. This is possible only if I assume F is regular. That regular plays an important role here. Since F is regular, every element can be written in this form. That is the regular definition. Okay, x is equal to xax as well as y equal to yby like this. What about a and b? They are elements in F. F is regular and in this I am taking this. Okay. Can you imagine this AX? What is that AX? And AX is an idempotent. Idempotent means what we have to prove? Ax the whole square equal to Ax. Ax whole square means Ax into Ax. Associative property if I use A instead of if you imagine A here, Ax, then Xax is nothing but X. Therefore, result is going to be Ax. Therefore, Ax as well as By are idempotents. I think easily you can follow that. Okay. Ax and By are idempotents. If F is regular for each element X, I can find an idempotent element like this. Now, this is also an important result. What is that? Fx can be written like this. Fxax. Normal set theory concept, that is Fxax is a subset of Fax, that is a subset of Fx. That means they are all equal. That means we need Fx is equal to Fax. Whenever F is regular, we can say Fx is equal to Fax. In the same manner, Fby equal to Fy. If you remember these things, we can do a lot with this. That is, if it's a regular subnearing in a substable nearing, in this case, we will get Fx is equal to Fax and Fby is equal to Fy. Now let us use the previous theorem. What is that? If it is an idempotent Fe plus Ff, then I can write it as Fg, where G is nothing but E plus F minus Ef. Therefore, since Ax, By are idempotents, we get, okay, what we have proved? Fax is nothing but Fx. Fby is nothing but Fy. Therefore, instead of Ax and By, I can put simply X and Y. That is the corollary. Fx plus Fy is nothing equal to Fz. Just I want to stop sharing and I want to see the comments. Just a minute. I want to share the chat messages. That's why I come out and thinking. Really, is it interesting or not? That is algebra. Are you in this? Any response from the participants? Dear participants, really interesting. Can we proceed? Thank you. That is algebra. You can follow me, so I'm very happy. Okay. The another lemma. If n is substable nearing, okay, n is a substable nearing. If f is a regular subset of n be a substable nearing and f is a regular subset. What we got? F has no non-zero nilpotent elements. That means f is reduced. N is reduced. We have defined here in this. In that similar manner, we got this result. F has no non-zero nilpotent elements. The second result we got in lemma 1.1 is whenever AB equal to 0, then BA equal to 0. Yes, ma'am.
Ma'am, kindly share your presentation, ma'am.
Oh, sorry. Thank you.
Yes, ma'am. Thank you, ma'am.
I forgot to share.
And participants have shared their comments, ma'am.
Oh, sorry. Okay, but to see the comments, I came out, isn't it?
Yes,
After that, I missed it. Okay.
They have responded, ma'am.
Okay, thank you.
Okay, ma'am. Thank you, ma'am.
Now is it visible? Let
Yes,
us
ma'am.
ma'am. Okay, ma'am. 1 minute.
Yes, ma'am. Thank you so much.
Okay, thank you, ma'am.
Thank you.
At any time, any participant can stop me. If I'm boring, I can switch over to some other interesting results. That's why I'm asking. I think the results will motivate you towards algebra, I think.
Yes.
Okay. Thank you, ma'am. Okay. Whenever n is a substable nearing. Substable means we have AB equal to 0 means BA equal to 0. That is very useful result for us. AB equal to 0, then BA is also equal to 0 when F is a regular subset of n. Okay. Next one, n is a substable nearing and I is an ideal of n. In that case, AB is an ideal of I. AB is an element of I implies A and B is also an ideal of I. In this manner, we have defined what strong IFV we have defined, isn't it? That is for all elements in N, if it satisfies means we say that as strong IFV. Similar to this, for the F subgroup, I am able to insert one element. Very sorry, it is going. AB is in I, then A and B is also going to be in I for any ideal. That is, it is true for all the ideals. I be an arbitrary ideal. I be an ideal of n, I can prove it whenever n is a substable nearing. Okay. Substable nearing is equivalent to what? If I go and search for that, means we will get these results. When n is a regular and V-commutative, regular as well as V-commutative. V-commutative, you might have remember, the first element alone is fixed. In that case, n is regular and V-commutative, and A is an invariant subgroup. Invariant, you can remember that. Invariant subgroup. If it is true, in that case, our substable nearing is going to be equivalent to what? The set A, that is, n is substable with the stabilizing subset A means I can use this result. Ax is equal to xax. N is substable under these conditions means in the same thing. N is a regular, I'm saying theorem 1.4, that is N is a regular V-commutative nearing and A is an invariant regular. Here we have introduced regular subgroup of N. Then we are able to prove these results, that is for all x in N. Very sorry. Where to go? Okay. For all x and y in N, Ax intersection Ay. Okay, Ax intersection Ay is equal to Axay. That is also equal to Axy. That is equal to Xay. Anything we can change like this. That is, whenever A is an invariant regular subgroup of V-commutative regular nearing, we are able to say that is equivalent conditions for substable nearings. I think let us prove one theorem. This one. Theorem. What it is? We are going to prove some set is nothing but Boolean algebra. Many of us today think about application means direct real life application. Not like that. Nearings is having direct applications also, but various types of nearings are there. They are having direct applications. I can say that is this one. Planar nearing is having direct application in block designing, etc. Similarly, many applications we can point out, that is in fertilizers, designing the fertilizers also nearings is used like that. Many applications we can say. You can see everything in the nowadays it is possible in that, isn't it? Google Chrome or in any search engine, you can even from chat GPT, you can get all these results. What I'm trying to say here is nearing, substable nearing is, from that substable nearing, I can form a set which is a Boolean algebra under useful set inclusion. That is, our set of all F subgroups is going to be a Boolean algebra. Mathematics is interconnected, isn't it? Or that is, we are mainly having branches, main parts in mathematics. Algebra is the main thing we are. I'm doing research in algebra. That's why I'm saying algebra is the main. Algebra is strongly connected with every other parts of mathematics. That is nonlinear differential equations, nonlinear functional analysis, nonlinear. What else we can say? In many ways, it is linked with each other. Okay. Okay, assume that F is a regular substable nearing. We are taking with regular substable nearing. F is an invariant regular subnearing. F plus is an abelian. Like that previous corollary and that theorem, we are assuming these things. Under this condition, we are able to prove the set of all F subgroups is a Boolean algebra. To prove a Boolean algebra, what we have to do? We have to say distributive lattice. Sorry. What we have to do? Relatively complemented distributive lattice. Like that we have to prove, isn't it? We need meet and join function. Instead of meet and join function, we are going to use in set inclusion. What we can use? Intersection as well as addition. Like that we are going to use. Now, what is our assumption? F is a regular nearing. If F is regular, then I can write x is equal to xax and y is equal to yby. I have assumed one more element z in F that can be written as zz for some ABC in F. Whenever F is regular, these are all possible. Regular definition. And then we have discussed what about AX, BY, AX, BY and CZ, they are going to be idempotents. Okay, they are all idempotents. And the basic result we obtained is the set of all idempotents commutes with all the elements of F. Whenever N is a substable nearing, we can say this one. We are going to make use of these results and get some preliminary results. What does that means? AX BY is also an idempotent. Similarly, AX CZ is also an idempotent. Okay, see the proof. AX BY into AX BY. Isn't it? Just I am using associative property. And since AX and BY are idempotents, they can be interchanged, they commutes. Now group the things, that is AX is an idempotent, BY is also an idempotent, we get this. Okay. Now, sorry, I go fast. Okay. Another observation. Whenever F is a regular nearing, Fx is equal to Fax. Similarly, Fy is equal to Fby. Fz is equal to Fcz. These things we have observed from the previous theorem. Okay. And in the corollary, what we have observed, Fx plus Fy is equal to Fz. Whenever x and y are elements of F, x and y are elements of F. Sorry, I have made a mistake in this. Sorry about this. X and y are elements of F and Z is an element of F. Okay. What we are going to prove first? First, we are going to check whether it is a distributive lattice. To prove that a distributive lattice, meet and join function, we can use, isn't it, intersection and then Fy plus Fz. That means Fx intersection Fy plus Fx intersection Fz. Okay. Instead of x, we are going to use ax. Instead of y, by. Instead of z, cz. Why we are using this? Since they are idempotents, they are equal, and we are making use of the previous theorems. We have proved, isn't it? If f e plus f means I can write it as by. Yeah. E plus f minus ef, like that we can join. Therefore, we are using this. Okay. And then previous theorem, whenever idempotent, what is that? We have proved one equivalent condition. Fx, this one. Ax intersection ay is nothing but axy. We have seen one theorem. Using that, I have combined these things. And then since idempotence, set of all idempotents is a subset of this Ft, that means satisfies both the distributive laws, we can say. Therefore, I can multiply like this. This distribution is also defined in our right nearing, since it is an idempotent. Remember that. Similarly, how we are getting this one? Can you understand? Ax by, and then we are introducing one ax. That is, instead of ax, I can put ax into ax, and then I have commute with this by, and it brings to this side, means this one. That's, we are playing with variables with certain conditions. Okay, this one. Fax can be written as, we have seen one theorem, isn't it? Shall I once again see this one? Ax intersection ay is equal to ax ay as well as axy. That's why we are writing like this. What? Intersection, this one, axy can be written as ax intersection ay. And then ax is nothing but x, that is, sorry, fax is nothing but fx. We have equation number 3. Fax is nothing but fx. Therefore, I can change ax, by, and cz as xyz. We have proved the distributive lattice property. Distributive lattice property is over. Next one, what we have to prove? This one. Complemented property, this one. Oh, sorry. Whenever fx is a subset of fz, that is a subset of fy. Fx subset of fz, that is a subset of fy. What we have to prove? We have to get one subset of one set fz satisfying fz intersection fw is equal to fx. Yep, I am able to find a set fw in this manner. Fw intersection fz is nothing but this fx, and that fw plus this fz gives this fy, means we can say that is a Boolean algebra. For that purpose, in the same manner, we are doing fx, fz, fy, we have assumed. Instead of x, y, z, we are taking the idempotent elements. Since it is an element, ax is an element of fax, that ax can be written as, it is a subset of cz, it is a subset of by, fby. Therefore, we are getting these things. Again, we are playing with the numbers. Instead of ax, I am putting n1 cz. Cz is an idempotent, therefore we can combine. Therefore, AX is nothing but AX CZ. In the similar manner, AX can be proved equal to AX BY. These things we are able to get. AX CZ, CZ AX, AX BY, BY AX, everything is equal to AX. As well as CZ BY, BY Z, both are equal to CZ. Using these things and defining one W like this, AX plus BY minus CZ, in this manner we are defining. In that case, we are able to get our required result. That is, that FW intersect with the FZ means we will get Fx. If it is added with, that is FW is added with the FZ means we will get Fy, like that. For that, we are checking whether W is an idempotent. W is an idempotent. For that, these calculations we are using right distribution law alone. Therefore, I have written like this. Since AX, BY, CZ are idempotents, we have commuted. Okay. And we are proceeding. AX, BY, CZ are idempotents. Therefore, we are able to get W is an idempotent element in F. The other things are easy. The same concept we are using, that is AX, BY, CZ are idempotents. Therefore, we can easily get what? CZ plus W minus CZW. Here W is also an idempotent. CZ is an idempotent. Yeah. We are substituting the value of W and doing the expansions and simplifications. And we are getting that CZ plus W minus CZW is nothing but BY. Okay, addition of these things, CZ and W are idempotent. Therefore, because of that theorem, E plus F minus EF, like that we have proved, isn't it? That theorem we have used. That means what we have completed, it is a relatively complemented distributive lattice, that is nothing but a Boolean algebra we have obtained. Ideals in substable nearings is very separate topic. We can discuss more on ideals. I'm not going into that. Let us see some light things. Okay, equi-commutative nearing. See that's the definition. Equi-commutative nearing. Yep, how it is defined, let us see. XA equal to XB implies what? AX is equal to BX. This is one definition. Equi-commutative nearing. XA equal to XB. The first element is X. The second elements in both the sides are varying. If it is equal means we can write it as AX is equal to BX. Using this definition, what we can get means, see that proof. First thing is, if it is an equi-commutative nearing, then it is zero symmetric. To prove zero symmetric, what we have to prove? N 0 into n is always 0, we know in a nearing. We have to prove the reverse case. N into 0 is also 0 means it is going to be zero symmetric. 0 into n equal to 0, we know. That 0 can be written as 0 into 0. The first elements are same. Therefore, we can use, since it is an equi-commutative nearing, n into 0 equal to 0 into 0. We get that zero symmetry. Okay. That is, if it, by the definition of equi-commutative nearing, we can say n is going to be zero symmetric if it is equi-commutative nearing. This lemma I have discussed here earlier, you might have remembered that a square equal to ab and a square equal to ba. If equal to ab like a equal to b like that, we have discussed. Here, the similar result we have tried This one, that equi-commutative nearing. Whenever a square equal to ab, that implies what? A square is equal to ba. That is also simple interchange, isn't it? A square is nothing but a into a is equal to ab. The first elements are same, therefore we can interchange according to equi-commutative property. Therefore a square is equal to ba. What is that one? Ab equal to 0 implies ba equal to 0. How we are getting this? Same thing. 0 can be written as a into 0. Why? Because of that zero symmetric property. Otherwise, we can write only 0 into a. Normally in nearings, since it is equi-commutative, we got it is zero symmetric. Because of that only, a 0 can be written in this fashion, a into 0. Here we are having a, therefore we can select a here, like this. ba is equal to 0a, like this we can get, like this. Equi-commutative nearing means we are able to get small results like this. Based on that, we can prove very big theorems. If n is an equi-commutative nearing, if n is regular and I is a proper ideal of n, then every element of I is a zero divisor. Zero divisors we have defined in ring theory, isn't it? AB equal to 0 implies either A equal to 0 or B equal to 0. In the same manner, here also we get one result. If n is an equi-commutative regular nearing with identity 1, we are able to get these results. That is, n has no non-zero nilpotent element. Has no non-zero nilpotent elements means if it is reduced. And n has star IFP. That means AB equal to 0 implies A and B equal to 0 as well as BA equal to 0, like that. Each idempotent is central. Let us see the proof. What is the first one? It has no non-zero nilpotent element. How we are using that equi-commutative property? See here. We have assumed n is regular. Therefore, n can be written in this form, a equal to axa. That can be written as a into 1. With identity, we have selected. Therefore, multiplicative identity exists. Therefore, a into 1 is equal to this one. The first element is a. Therefore, we can interchange using the definition of equi-commutative nearing. That means what we have, we got a is equal to xa square. A square is 0. Why we have assumed a square is 0 first? Can you understand now? We are trying to prove A has no non-zero nilpotent element. Nilpotent means A power k equal to 0 for some k. Therefore, we have assumed A square equal to 0. What result we got? A equal to 0. Therefore, there is no non-zero nilpotent element in our case. The second result, what we have assumed, n has star IFP, we are trying. Star IFP means AB equal to 0, we have to assume. We have to check whether BA equal to 0 as well as A and B equal to 0. Let us see, AB equal to 0 means it can be written as A into 0, since equi-commutative nearings are zero symmetric. Okay, just using equi-commutative property, we can write AB as BA. This one, by interchanging, we get BA equal to 0. Whatever A and B equal to 0, directly it is difficult to prove A and B equal to 0. We are going to make use of the first one result. That is, it has no non-zero nilpotent element. Therefore, I am trying what is AN square. AN square value is equal to 0. Because of that previous one, I can easily say A and B must be 0. That means star IFP property. AB equal to 0 implies BA equal to 0 as well as A and B equal to 0. Okay. The third one, each idempotent is central. Let us see the proof. Idempotents are central. That means what? It commutes with all the elements of n. A equal to En and B equal to Ene, we are assuming. That is the main thing we have to remember. A equal to, algebra is normally like this, isn't it? To prove one certain result, we have to assume or take some element like this. A equal to En and B equal to Ene. Now, AB and BA are equal to this one. AB equal to B square and BA equal to A square means A and B are equal. We have seen one basic lemma earlier. Because of that, we got En is equal to Ene for all the elements Ene. That is for all the idempotents and for all the elements N in capital N, it is true. In equi-commutative nearing, we are able to get this. And then says this one, can you accept this 1 minus E into E? That is right distributive law. E minus E into E is nothing but E. E minus E is 0. Therefore, 1 minus E into E is equal to 0 implies, what is that? I'm inserting one element in between. That is the second one. Insertion property holds, therefore, AE 1 minus E into AE equal to 0. Now, let us multiply distributive law. Let us apply distributive law. We are getting this. AE is equal to EAE. Already we have proved this. Equal to this one. Okay, equation number 7 and the last one we have using. Therefore, all the idempotents commutes with the elements of N. That is, idempotents are central. Let us quickly go through that. 4th and 5th one. Okay. This, what result we have to prove at the end? NF plus NE, where E and F are idempotents. We are going to prove this result. That means we are going to take an element here, prove it that both are inclusions we have to prove, isn't it? This one is a subset of NF plus NE, as well as the other case we have proved. NF plus NE is a subset of this one. Sorry, we are running out of time. Two slides, let me complete. Okay. Okay, this one, another interesting definition alone is enough, I think. Pseudo-commutative nearing. X, Y, Z is equal to Z, Y, X. How it is defined? For the V-commutative law, V-commutative property, first element is fixed. Here, the second element is fixed. Based on this, we can get many results, lots and lots of results in that one. Like this, playing with numbers gives lots and lots of results. Those results are not simply theoretical one, they are having real applications. With this, let me conclude my presentation, I think. Please ask your questions. Let me see your any queries.
Participants, thank you, ma'am, for your thought-provoking presentation. Participants, now we open the floor for questions. If you have any questions or further clarifications on today's topic, feel free to ask.
I have discussed only about nearings. We are having semi-nearings, gamma nearings, and gamma semi-nearings, normed nearings, planar nearings. Many types of nearings are there.
Ma'am, shall I ask the question, ma'am?
Yes,
In
ma'am.
YouTube,
Yes.
um, how do you think nearing theory can be applied to solve real world problems?
Ma'am, that is okay, ma'am. Let me explain.
Hmm.
Nearing, nearing theory, direct nearing theory is directly applied in different fields. That is, it is non-linear differential equations to solve non-linear differential equations problems. Now, nearing theory is used. Means, can you imagine differential equation is having direct applications in many of the cases. Similarly, functional analysis, similarly, numerical analysis, in everything, nearing concept is used.
Okay, ma'am.
And the same manner, in the near fields are used for cryptography and then coding, that is what is that? Correcting the errors. Yeah, everywhere it is used, ma'am. You can see the applications in the net. That is the that is evidence are there.
Okay, ma'am.
Mm.
Thank you. Okay, ma'am. One more question, ma'am.
Yes, ma'am.
What are the current research trends in nearing theory?
Nearing theory, that is
Current.
current everywhere. That semi-nearings, research, recent papers. Last year also we can see. Similarly, Smarandaki, isn't it? Smarandaki nearings like that. Papers are going on, and then. Satyanarayana Reddy is doing research in gamma nearings and then normed nearings, planar nearings. The researches are in all the fields of nearings, ma'am.
Okay, ma'am. Thank you. How do they relate to other areas of mathematics? Can you give an examples for anything,
That
ma'am?
is a vast one. Means nearings concept. First we have to understand. Then only we can relate it to the nonlinear differential equations directly. We can apply. Uh, at present, I am not having. I think 1 minute.
Okay, ma'am.
Let me check. Hmm. Let me try this. I'm not having the whole thing, but the problem I'm having. Can you see this?
Yes, ma'am.
Okay. Let me maximize this. This is one application. How it is related, you can imagine.
Okay, ma'am.
You want to test combinations of ingredients for fertilizers. There are different types of fertilizers. What is needed for our sand? Like that, we have to choose a correct fertilizer. In that, we are defining using that nearing with specific operator. That is, we are defining one binary operator like this. Based on that, which ingredient we need. There are totally 7 ingredients. Out of that, what all are we need for that purpose? We need a nearing theory. Okay.
Thank you, ma'am.
Similarly, in differential equation also we are having. At present, I couldn't take, but
Okay.
everything is available in the net, ma'am. I have
Okay.
taken all these from the net only.
Sure, ma'am. Okay, ma'am. Thank you, ma'am.
Yes, ma'am. Welcome, ma'am.
Thank you so much, ma'am,
Yes.
for the wonderful session. Now I request Dr. L. Pandiselvi to propose the vote of thanks.
Yes, ma'am. Good evening, one and all. First and foremost, I thank the Almighty God for blessing us with this opportunity to learn new concepts. We would like to extend our sincere thanks to our Secretary, Sri APCV Chokkalingam, for his unwavering support and guidance throughout this endeavor. We are grateful to our principal, Dr. C. Veerabahu, for his visionary leadership and encouragement. Our heartfelt thanks to our head of the department, Dr. C. Deva Manoharan, for his tireless efforts and dedication to making this day a success. I extend my heartfelt thank to our resource person, Dr. S. Uma, for sharing her knowledge with us today. Thank you for the enlightening presentation, ma'am, and we appreciate the time and effort you invested in preparing for this program. We also appreciate the engaging questions and discussions during the question time. Finally, we would like to thank the faculties and scholars from various colleges from different states. So, finally, thank you all once again for your presence, participation, and contribution to the success of this FDP. Thank you, one and all.
Thank you, participants, for your patient listening. I think some of you might have turned into algebra. Doing research in algebra is not an easy job, but playing with numbers is an easy job, isn't it? We can do a lot in algebra and we can achieve a lot. That is the nowadays the applications mean most of us thinking about the direct real life applications, but nearings is having many very good combination. It is having very good applications with our other parts of mathematics, and we can do a lot. Thank you for this opportunity for each and everyone in the V.O.C. College. Thank you.
Thank you, ma'am.
Thank you so much, ma'am, for accepting our invitation.
Thank you, ma'am. Thank you, sir.
Thank you, ma'am. Thank you.
Thank you.
Dear participants, we have shared the feedback link in the platform, and we will check. Some of you have posted that the link has not opened. Maybe by mistake, it is J3 feedback. We will check it over and we will rectify it as early as possible. Thank you. Thank you, ma'am, for your valuable time.
Thank you. Thank you, sir. Shall I leave now?
Sure, ma'am. Sure, ma'am. Thank you, ma'am.
Thank you, ma'am. Once again, thank you so much, ma'am.
Thank you, ma'am. Thank you.
Participants, kindly wait. I'll post the feedback link. Kindly wait for a minute.
Dear participants, the J4 feedback link has been posted in the comment section in both the platforms.